Hi, I'm going to walk you through my session called Thread Parallelism. And this session is part of the Advanced Day, where I have already discussed parallel programming in general. There are three forms of parallel computing. The three most important forms for this course are a single-threaded program. Then if you want to scale up, if you want to use multiple cores, you use thread parallelism, which is this session. And there's also distributed parallelism, where you can scale up to include multiple computers, multiple nodes in multiple countries. But this session is about thread parallelism. And the goals of these sessions that you can explain, that you can schedule jobs with thread parallelism. You can explain how these jobs are scheduled. You can explain how code of your language makes use of this, like which keywords are important. You can show the results of a correct benchmark, but you can also explain the results of a benchmark where something's off. And you can argue why you should stick to your programming language, even if it is not the fastest. So, why thread parallelism is important? Because it is one of many ways to speed up the calculation. And I discussed this in an earlier session. If your calculation takes 11 days and your code already has this, then it's just a couple of characters away to use it. To get below this 10 days so that you don't need to save. You can just run your calculation, and it will be less efficient already if you use multiple cores, but still sometimes your time is also a resource. Good. So in this session we are going to benchmark. Let's make it a bit bigger. Let's make it even bigger. In this session we're going to benchmark thread parallelism, as we should not make claims about performance without measurements, and there's a resource here. And this whole setup is like 1, 2, 3 scripts, and we can already see in the table of content here. There's a benchmark script, a slurm script, and a language script. And there's a flow of information through these scripts where the user supplies his or her account and his or her favorite language to the benchmark scripts. This benchmark script, it's only one, will supply information, which is the account to schedule on, the language that's favored for the user, and the number of cores that will be used. And this number will go up. It will vary from 1 to 64 in this case. Then it will run a slurm script with that information. That can be for different numbers of cores. There will be many slurm scripts being run. Can be 16 or sometimes 64 slurm scripts will be run. And that slurm script, which is will call then either Julia-MATLAB or R, whatever your favorite language is. It knows because it knows your favorite language. Good. What I'm going to do is now I'm going to start from big to small. So I'm going to go through the benchmark script there, and then work my way down to the details. So let's take a look. Benchmark to the integration. I can click on this, it's a link. Is the script that starts a benchmark by submitting multiple jobs to the slurm queue using the slurm script below. The goal of the benchmark script is to do a fixed unit of work with increasingly more core. If the script itself only does light calculations, you can run it directly. Here is how you call the script. Alright, so you need to do bash, name of the script, then the account you want to book it on, and then your language. Good. And look, for example, what this looks like here. Also, the script is quite helpful. If something is off, this script will give you a proper error. So this is how you call the script. You're going to benchmark on someone's account, like someone's HPC account, to book the core hours with for some kind of language. The slurm script it is actually what's being scheduled. So the previous script will schedule this script and will run them. And the goal of that script is to submit a calculation that uses thread parallelism with a custom amount of cores. So it will run a calculation with 1 or 2 or 3 or 4, etc. amount of cores. It's called by the benchmark script, so not by the user. Also, if the Slurm script is not downloaded yet, the benchmark script will try to download it for you. If you cannot download your stuff, here are the 3 scripts. You can click on them and you can see them and it will download there. So here we see a script being downloaded. Each of these Slurm scripts are called by the benchmark script, where the benchmark script supplies the desired number of cores. So the Slurm script knows, this script knows how many cores it will use, or it needs to use. Alright, so this Slurm script will call the right language script, and this is where the action happens. It performs a job with thread parallelism in your favorite language. The goal is to have a fixed unit of work that can be done with a custom amount of cores. This language script is called by the Slurm script, not by the user. Also, if it is absent, the benchmark script will try to download it for you. So the benchmark script does a lot to help you out. If you need to download it, then here you can download it too. Alright, let's take a look at the exercise. I'm going to take a look at the table of content first here at the left. Start the benchmark, read the benchmark script. So read the script, so we're going to read the scripts in details. We're going to share the results, analyze results, compare to other. Job scheduling problem, there are extra exercise 1 and 2. And where to go next and some troubleshooting. And here are some errors, the reference to the literature. Sure. So now I'll walk you through the exercises. Exercise 1. Start the benchmark on your HPC cluster. The goal of this exercise is to start the benchmark script on your HPC cluster as well as some troubleshooting. On your HPC cluster, download the benchmark script. I know I need to use wget. I just copy, paste this command. So I need to download this on my HPC because this means I'm going to move this window to the left. Yeah. This is where I am. And at the right, I'm going to go to a cluster I'm already on. So this is Pelle, whatever that is. And I copy paste this command to Pelle to download this script. And if I take a look at all my files by ls, I see that there's a script here. Good. Next step, run the benchmark script. Well, I know how to do that. You need to do bash and then the name of that thing. And then it's running. Error. Incorrect number of arguments when calling. Please supply all 2 arguments. Account and language. Alright, so I'm going to do staff R and then it will run. If you don't know any account, you can use proinfo. Or what's it called? Proinfo. Well, in Pelle it does not have proinfo. Most clusters have the thing called proinfo, and then you can see what you can use. I'm going to use my staff account here, and I'm going to use the R language. There. And it's done. It has submitted a lot of jobs. If I do SQ list, oh, that's SQ me, I can see all the jobs being scheduled. And if I do ls, I see that there's already even output being produced. I also see an R script here, and I also see a bash script there. Both these 2 are downloaded by the benchmark script. How nice! Next, check the Slurm output files for problems. Well, so what I'm going to do, I'm going to cat slurm. I want to So cat is show on screen. And I'm going to just show on screen all the Slurm files. Let's see if there's something off. No, there's no error. There's no big fancy big things. This looks perfect. Good. Let's go to the next exercise. Exercise 2. Read the benchmark script. Now we have the time to figure out what to do. What's the most single important line in the script? So you can just download the script here. What I'm gonna take a look at it on my HPC cluster. I'm gonna use Nano to just scroll through it. And I don't like this enough, so I'm gonna indeed open it on my computer too. There, benchmark to the integration. There, we use a mouse pad to open it, and I put it at the right of the screen. So let's take a look at that funky script. The benchmarks are the parallelism, the script will blob. So the question is, what is the most important single line in this script? Start from the bottom. Let's start from the bottom. Schedule all the jobs. That sounds what its purpose is. And I guess then here it goes, counts, that's the number of cores go from 1 to 64. And then here it schedules the job. So as batch is scheduling a job, and this is what it's all about. And it schedules a job at some kind of account for a certain amount of nodes, for a certain amount of cores, and then running a script. Sure. For Dardel, which is another HPC cluster, it has a bit of a different setup. You need to specify a bit more. You need to do n tasks equal to the number of cores. You need to use the shared partition, but most of the things are the same. Good. So this line as batch, that's the purpose of this script. The benchmark will schedule the batch scripts. It will schedule the Slurm scripts. In English, describe what the line does. It will schedule a script with some nodes, some cores at the partition with some name. This line of code is part of a for loop. In English, what does the for loop achieve? The for loop achieves that the number of cores submitted will be 1, then 2, then 3, then 4, then 5, etc. The for loop achieves that the same calculation is scheduled to be done with 1 core, then with 2 core, then with 3. Well done, well phrased. Next exercise. Read the Slurm script. So the benchmark submits a Slurm script of your favorite language multiple times to the queue. What's the most important single line in this script? So for this I'm going to click on this link. It takes me to the table of the favorite languages. I'm going to pick R because I know in the course most of the people run R. But the answers you'll see are quite similar anyways, like the scripts are very similar. So I've now opened up the do R to the integration. So this is the batch script, or the Slurm script, to do a calculation using R. There. Let's go back to the exercise. What is the most important single line in this script? What is this script all about? So start from the bottom. Alright, that's super clear. R script. Then do stuff. Here is an R script being called that does a calculation. And then this is the number of processes, which is the number of cores. So this is the most important line. It runs an R script while letting the R script know how many cores it can use. Yeah, so if you take a look at this overview, I'll make it a bit wider that you can see how similar it is. Let's make it a bit smaller that you can see. Yeah. So you see that all the 3 languages have a similar line. They start with their language. Then they some need to specify the number of threads, some need to specify stuff that should not be there, or stuff that should not be there. Then they run a script, do 2D integration. In this case it's something special, it's also it's a MATLAB file, or an R script, and then they supply the number of cores. MATLAB is a bit special, so that doesn't have this, it has a tailor-made script just for it. So it creates a lot of scripts, each with 1 or 2 or 3 or 4 cores. And R also is the more straightforward one. Describe what the line does in general terms. I've just said that it runs a script with a certain amount of cores and no nonsense. Next exercise. Read the language script. So I guess we need to take a look at that language script. Oh yeah, and we've just done that. Oh no, we need to do this. So let's take a look at our language. Here we have an R script. Sure, and you'll see again for the 3 languages, the scripts are super similar. I'm going to use mouse pad for it because it's lighter. So now it's opening up. I have it here. Now yeah, this is an R script. And then I can go back to the exercise. Locate the lines of code that make the calculation perform in parallel. Let's take a look. I start from the bottom. Let's see, print out stuff, that's not important. Print out the result, that's not important. End time, sure, start time. Alright, so it's this stuff that's important. So it starts, it does stuff, and then it ends. That means that this is the parallel portion, and here we see percent do par percent, which indicates that this is run in parallel. What does, let's go back to in English, describe, oh, so let's take a look for the other languages. So this is what I've just found for you. In MATLAB it looks quite similar, it uses par4, Julia uses threads.addThreads. But also like the names, like worker index, it's all the same. So this is how you could combine, the variable names are quite consistent, and apparently it runs a function called integration 2D. In English, describe what these lines do in general terms. So let's take the most straightforward one. Well, they're all quite straightforward. It calls the function integration 2D in a parallel way for a specific grid size, whatever that is. But it also tells how many workers there are and which worker is going to do this one. If you take a look at MATLAB, it's the same thing. We have 1 to n workers. So it creates a work index 1, 2, 3, etc. 1 per core. It runs integration to do with the grid size, number of workers, worker index. For R, it's exactly the same. Sure, there's a bit of fluff around it, like this do par. But again, we have a worker index that goes from 1 to the number of workers, etc. What do these lines do? Well, I've just described that. Let's take a look at the answer. For each available worker, per worker, do a part of the calculation and combines the results. Yeah, that's a perfect answer. So it splits up the work over the workers. Locate the keyword that makes the calculation perform in parallel, or locate the word that, when removed, would downgrade the calculation to be single-threaded. Well, for Julia it's this, else if it would be removed it's a regular for loop. In MATLAB it's par4, because would this be 4, it would be a regular for loop. In R it would be for each combined with the do par. You can't see do par well, this is icon in the way, but percentage do par, that is the thing that does it. That's the most important keyword here. And that's just put in the schedule. Next question. The function that is run in parallel, that is the function integration 2D, is made suitable to be run in parallel. In English, describe which changes are made to make it suitable. So for this I'm going to take a look at the R code. So we see that for all three cases, integration 2D needs to know a grid size, which is a resolution, the number of workers and which worker. So it means that these two arguments are added to make it suitable. If it would be single-threaded, then all you need to supply is a grid size, which is an accuracy measure. What do these changes achieve? Well, the answer is that these changes allow the workers to do their piece of the work without communicating. When this function is called, it knows exactly what to do. And this does not overlap with others. It's just one nice unit of work that can be run in parallel. These changes allow each thread to know what it needs to know to run its part of the calculation. Well spoken. Bonus, do you spot the bug in integrate 2D? Is this a problem? Why would someone keep it in anyways? Yeah, there is a bug in there, and I think the answer is best because it's more visual. And it's in this part of the function. I'll show you the full function here. This is the R function. Here we see the integration 2D function. There. And here we see stuff that it expects to be true. That's great. Here we see an interval size, which is the amount of accuracy. It sums to 0. But these are the three lines where there will be an error. Just taking a look at, because it divides the grid size over the workers. So the units of work, it divides over the users, over the amount of workers. And then it rounds it down. And this is the case for all three languages. And this can be like a small round off, but it's still a round off. So the goal of this is to get into a nice round number, like an integer number. And then from that it tells where to begin and where to end. But this rounding off means that some indices will not be used at all. So just work that out in an example. And the best example, which is a quite trivial example, but it does make the best case, if we have a grid size of 3 and we only have 2 workers. That means if you plug in this code and we fill in the numbers, that the begin index for the first worker will be 1 and the end index of the first worker will be 1, so it will do the first of 3 pieces of work. The second worker will do the second unit of work, but the third piece of work is never done. So that means 1/3 of the work is not performed, and this will probably give an error, give like a sloppy error and like a rounding off error. However, the bigger the grid size, the problem gets less and less, because if the grid size is bigger, the amount of workers will fit in neater and neater. I kept this bug in for readability and also to see, to find out if you're sharp enough to see it. Also, this session is about thread parallelism and not about the extensive calculation of these indices. Good. Exercise 5. By now, some of the calculations in exercise 1 will be finished. If not, no worries, just continue. In the terminal of your favorite HPC cluster, run the following command to collect all the results. Well, let's do that. I put this to the left there. I go to my HPC cluster, close all this stuff there. I'm gonna paste this command again. Tick, tick, there. Alright. And copy paste these results to a shared HackMD document. So I select all this stuff. There's also a top. Control Shift C to copy from a terminal. And I'm going to paste these here in this shared HackMD document. So my name is Richel. I'm going to paste my results here. There. Done. The idea of this is that we all can collect our results, our benchmarks. Next step. Let's make it a bit bigger again. Analyze the results. So take it easy. Doing this analysis yourself is useful if you are fluent in analyzing data. If not, you are encouraged to use this spreadsheet or this R script. So you see, if we go to exercise 7, I have been using this R script to analyze the results before. But I'm going to show you how to use a spreadsheet, because not everybody knows R, so I'm going to show this in some kind of spreadsheet program. So let's take a look. Copy paste the results of the previous exercise into a comma separated file called my results. Sure. My results. So I'm going to make a file called mousepad myresults.csv. And I paste it. I save it and I close it. And also close this. Good. These are the descriptions. Alright, now we need to load this file. So I'm going to start LibreOffice. If you have Windows, you're probably going to use Excel. And I'm going to open this file. So for me, it was in the home folder. It was called My Results. It's a comma separated file. This will be picked up by LibreOffice and probably Excel too. And here I have my results. I will need to sort for the number of workers to be 1. Let's do that. I think that's neater. Sort. Options. So the first row. The first row is a header. Range contains column labels. Sure, yeah, this is what I needed. And I'm going to split for the number of workers. And probably I need to say that it's the natural sort, because then 1 gets at the top. There. Here we have our results in a nice ordered fashion. Add a column called wall clock time, which equals course seconds divided by n workers. Alright, for this exercise I just made my own spreadsheet, but now I'm going to use this spreadsheet. Can I download it? No. Alright, so I'm going to open this spreadsheet anyways. Where I have it there. And I'm going to just paste the stuff that I just made here. I'm going to paste this to the spreadsheet that you can download. There. And let's take a look what we got. Add a column called, well, no, I need to do it myself. Sure, I'll do it myself. But we can already see the results here. Add a column called, what was it called? Wall clock sec, sure. Oh, well, I'll write it, wall clock sec, sure. Which equals core secs divided by n workers. Okay, sure, is core seconds divided by number of workers. Done. There we have it. Let's make it nice and equal. Add a column called speedup. Speedup. Which equals the wall clock time for one core divided by the wall clock time for that amount of cores. The wall clock time for one core, divided by the wall clock time. No, let's do this one first. This is the wall clock time of one core divided by the wall clock time there. And then this row 2 needs to remain row 2. If this works, then the speed up should be 1 here, there, and it should go up. Let's double check. Okay. Yeah, it goes up. Well done. Plot the speed up on the y-axis per number of workers on the x-axis. Plot the speed up, number of workers, insert chart, make it into a scatter plot. And here, this is the number of cores, this is the speed up. And we can see that because the number of workers or number of cores goes to 64. And the speed up goes to 30 or something. Yeah, 24. 24, but also sometimes higher. Good. So this is the speed up. There, well done. This is how it looks like. What do we need to do more? Compare your speed up with the Amdahl's law figure of the previous session. Take a look at that session then. It's here. And put this to the right, put this thing to the left, and what do we see? Oh, this is a bit big, this is a bit big. So what do we see? So we don't see this flattening off yet. It's just not clear enough to see anything from happening. So it seems to maybe go a bit slowing down, like. But it's hard to see what it's doing. So I think the parallel portion is quite high here, because else you would see it flatten off. It doesn't flatten off at all. So that is an answer. So we just don't know. It doesn't flatten off enough. If we would see it flatten off, then we would say, all right, then we can easily determine the parallel portion. So that is the answer here. What do you estimate to be the maximum speed up? Well, we cannot estimate this because there's no flattening off. What do you estimate is the percentage of code that can be parallelized? We don't know, but it's a high percentage. Basing on the Amdahl's law figure, we don't see it flatten off at 64 at all. So maybe it's like 95% or even higher. We just don't see it. We just don't see it. Good. Exercise 7. Compare to others. Compare your results to others that ran the same benchmark, yet for other HPC clusters and other programming languages. Let's take a look. What have we got here? So there's a there. Let's make it a bit on one page. Total core seconds, efficiency, speed up. So speed up is what we've known already. We have discussed efficiency and total core seconds in the previous session, so I'm not going to repeat that. So we see the speed up. Like for Julia, this flattens off, where for R, this is still going up. So this seemed, and we just discussed that for what we found here. We know for this was an R example on Pelle. Is Pelle here? Yeah, Pelle is here. We found this line probably again. And we don't know where it will flatten off yet. We need more. We need to run more. So this means this is quite super parallelizable. This means a high percentage of the code can be run in parallel. If you take it the same code in Julia, this is way less because we see it flatten off here. What MATLAB is doing, I'll come back to that later. If you take a look at the total core seconds, so this is the total amount of cores being used for the calculation, so all combined. We see that for R, like Cosmos and Kepner-Kaiser, they are at the lower end. This means that they are faster because they need less time to do the same calculations. Where Pelle is a very new cluster, so this can change. but Rackham here in blue is very old. But we know that you can see that these are a bit slower, like twice as slow. If you take a look, however, for the Julia language, then it gets more closer. We see that Cosmos is fastest here too. MATLAB, I will leave this in the middle for now. If you take a look at the efficiency, which is the percentage of cores being used efficiently, being like the opposite of waiting, then we can see clearly that Kebnekaise keeps things very efficient. It's even above 100%, which should not be possible, but the calculation gives this as a feature. So I've left it in. And we see that Pelle does worst here. Maybe because it's a new cluster, maybe it just doesn't deal well with shared memory. We don't know. But we do see that for MATLAB, the relative efficiency follows the worst line possible. And this is strong evidence that this code did not run in parallel at all. This probably means the code was single-threaded. That means it can only employ one core, even though many more were scheduled. And this is how it looks like. And if you take a look at the total core seconds, then it will look like a straight line. And it does not look like a straight line everywhere. Like there's some weird thing going on with Kebnekaise here with the green line. But MATLAB was it did not parallelize yet, and I left it in on purpose. Let's see other things I've missed. Oh yeah, Julia is 100 times faster than R. So let's take a look at the total core seconds. So let's say Julia takes around 10 seconds. So at the higher end takes around 10 seconds, whereas here for R it takes around 300 seconds. So that's 30 times difference. Yeah, HPC clusters, they differ. Also take a look at how well they parallelize. I think that is interesting too. Total core seconds is on it. Yeah, so the speed up is higher for the R language and way worse for Julia. So that means that Julia has parallelized less code, but it could be that the thread communication has more overhead too, or that goes hand in hand. We don't know here. So that's the most important. Now we do exercise 1, which is an extra exercise, which is called job scheduling problem. So you have just submitted some multi-threaded jobs to the queue. What went wrong here and why is this a problem? So I'll zoom in a bit. So here we see SQ, which shows your scheduled jobs. And something's off here. It's called do R2D. So this is apparently testing out the R script. It's done by me. Don't know what this means. It's running. Here is the problem. We see that sometimes there are 6 nodes being scheduled. And if you remember from the previous session, a node is a computer on its own, more or less. So that means that this calculation needs to talk over nodes. So you want a multi-threaded calculation to run in shared memory so that they can quickly talk with each other. Like the results, the workers, they can quickly talk to each other. If you have multiple nodes, the overhead, like the time lost by other stuff, the time lost by communication is higher. You don't want that, so this is needlessly slow. So what should have been done is that this user, which is me, should have specified to limit the amount of cores to 1 node. And sometimes you can and sometimes you cannot. On Pelle you can specify it now. But think about it. Don't forget to pick only 1 node. Now we're getting into the last question. Should we learn a faster programming language? Like as can be seen in the benchmark, some programming languages are faster than others. Like I think it was a factor 30 or something. This warrants the question, should you learn to program in the programming language that does calculations fastest? We know that the fastest theoretically, we know that the fastest language are theoretically fastest because they allow you to write machine code. You can't beat machine code. It's what the computer uses. So if you speak in that language, well, you can be just as fast, or even faster if you're smarter. Assembler allows you to program in machine code, but there are languages that allow you to insert machine code, to use machine code anyways. Most notably, these are C, C++, and Rust at the moment. So that means these languages are theoretically the fastest languages because they can write machine code. So to write fast code, should one learn those languages instead? And below this is a figure from a study in 2000, the reference is at the bottom of this page, and it shows the distribution of runtime speeds of a certain problem for different programming languages. So we have the runtime. So they ask a lot of people. Each dot, each circle here is a person that submitted a program that solved this programming problem Z1000, and that was for different programming languages. And for what was the relative speed? And because C is theoretically fastest, they put this at 1, and then we had all the other languages here. The paper has an advice to yes, no, to learn a faster programming language. What do you think the advice is? So taking a look at this figure, we see that the spread of a language, also from C, can be 1000-fold. So although C is theoretically the fastest language, the worst C user took 1,000 times longer for it than the fastest user. The solution, and what's recommended by this paper, is not to hop between different languages and learn a new programming language. Instead, get good in your language, like be this person at the left in all these languages. That will cost you less and will give you more. So that is the advice given. So the variance within a programming language is bigger than variance between languages. Instead of learning a faster language, learn how to be fast in your language. So maybe this paper does not convince you, yes. Like the Julia code is 30 times faster than the R code. Why would this advice still hold? The reason is because the R code and the Julia code neither are optimized. None of these are optimized for speed. Both Julia and R can call C code, and C is the fastest higher level language because it can call machine code itself. So that can bring both speeds down in a way we cannot predict, and it will be interesting to see how this benchmark would look like for optimized code. Last question. Are there other factors that decide which programming languages to use? If yes, name some. Well, one easy factor is that you already know a programming language. One other factor is that, well, maybe you need a specific library or package for your field that is only available in that language. Maybe when starting out you have a colleague that is willing to teach you. Use that. Use that colleague instead of going out on yourself, especially for your first programming language. And sometimes you just need to work from code that has been written by someone else in a different language. So with this, I've talked about thread parallelism now. If you want to scale up, then distributed parallelism allows you to do a calculation on many computers. Sure, the overhead will be bigger, but you can also scale up more. With that, I've gone through this lecture about thread parallelism. And we have scheduled jobs that use it. We have explained how these are scheduled. We've seen the code and the keyword and the function and the modifications to the functions to use thread parallelism. We have seen the results of a correct benchmark and also a benchmark where something was off. And you can argue why you should stick to your programming language even if it's not the fastest. With that being said, I end this session and I wish you a very good day. Bye!